Hey, hello everyone. My name is Jongho Lee. I'm currently an assistant professor in the civil engineering department at UBC. I've got PhD in the mechanical engineering at MIT. Then I worked as a postdoctoral fellow in the chemical and environmental engineering at Yale University before I joined UBC. So my current research focuses on membrane-based separation technologies for water treatment and resource recovery. So today I'm going to briefly talk about some emerging membrane technologies for zero or minimal liquid discharge and resource recovery from wastewater. Just directly going to the point, mining is the water-intensive process, and wastewater is inevitably produced in large volumes. So mainly driven by environmental regulations, mining industry is more and more required to reduce their effluent to the environment with lower contaminant levels. But not only in mining, but also in general, so-called zero liquid discharge or minimal liquid discharge is more and more adopted, with targets to maximize the water recovery from their wastewater and recycle. This ZLD or MLD process minimizes the discharge of the wastewater and the water intake from the environment, and the produced solid waste is easier to truck and dispose. Therefore, the treatment cost can be reduced. And also, the mining process water and its concentrated form is also a good source for valuable resources such as lithium, copper, nickel, acid, gypsum, and so on. So today I'm going to briefly talk about some emerging technologies for ZLD or MLD, as well as resource recovery that our group at UBC has been working on. So the ZLD or MLD is essentially coming down to the desalination technology, because as we squeeze water from the wastewater becomes more and more saltier. So if you look at this charge, then this x-axis is showing a salinity concentration limit, which means that this is the maximum salinity of the wastewater that each treatment technology can handle. Then this axis is basically showing how much energy that each technology is requiring to produce fresh water. So as you can see here, currently the state of the art the technology for desalination is reverse osmosis. So the reverse osmosis is very energy efficient. But the problem here is that the reverse osmosis cannot handle more than 70,000 ppm of salinity, which is about twice higher than the seawater. So it cannot handle very salty industrial wastewater, such as mining wastewater, for aiming for ZLD. There are also other thermal distillation technologies that can handle much higher salinity wastewater, such as brine crystallizer or brine concentrator. But as you can see here, the energy consumption of this thermal technology is much higher than the reverse osmosis. So the question is whether there is any technology that can bridge this gap together. There is an emerging technology called the membrane distillation, which is a hybrid process that combines both membrane technology and thermal distillation technology. So in this membrane distillation, MD, a hydrophobic porous membrane is placed between the hot feed wastewater and cold permeate fresh water. And because of the hydrophobicity, only water vapor can go through this membrane. Then the temperature difference between these two reservoirs drives the water vapor from hot to cold side. And this process has several advantages. First, the salt rejection is very high because this is basically a distillation process. So salt doesn't evaporate, and that's why we can reject salts very effectively. And also the salinity tolerance is very high. So this process can handle much higher salinity wastewater compared to reverse osmosis. And if you can use the low grade heat, such as waste heat, the energy cost to heat up this part of the wastewater can be very low. And because of the nature of membrane process, the physical footprint of the process is very small. So even with these advantages, like other membrane technologies, the membranes are prone to fouling. So fouling means the membrane becomes contaminated because of all those organic or other dirty stuff. So we have been working on developing membranes that can work in that membrane distillation process, but very robust to fouling. So for example, we used a conventional hydrophobic membrane that is used in membrane distillation process, and we placed the crude oils as a model foulant. So after we placed these oils, the crude oil on this membrane surface, we immersed this membrane into water. And as you can see, this oil just spread and then stick to the membrane surface, which means that this oil basically fouled the membrane. But and on the other hand, this is our membrane that we developed to prevent membrane fouling. So again, we placed the same crude oil on this membrane. We call this membrane Janus membrane, and then we immersed this membrane in the water as well. So as you can see, these crude oils were immediately detached from this membrane surface, showing very excellent fouling resistance of our developed membrane. So we used this Janus membrane to the membrane distillation process like this. So as a source water, as a feed water, we prepared this very dirty crude oil in saline water immersion as a model dirty water to desalinate. And we first tried conventional hydrophobic membrane. We can easily available, which we can easily get from the market. Then this is so this y-axis is the water flux. So basically because of the fouling, we can see the water flux declines. But when we used our Janus membrane, we were able to see the consistently high water flux without any fouling. And at the end of the day, we were able to get this clean water from this dirty water. Okay, so let me just briefly switch the gear to the resource recovery side. Actually, our group has been working on resource recovery from municipal or dairy wastewater. So especially today I'm going to show methane recovery. So even though methane is not a prevalent contaminant in mining wastewater, I think that this is a good example to show how our technologies can work and also applicable for mining wastewater as well. So just briefly, the methane is a problematic gas in wastewater sector, but actually it's a good primary constituent of natural gas. So for example, in Sweden, 86% of natural gas vehicles are running on biomethane produced from wastewater sector or the food waste. And then those biomethane is also supplied to the household as well. So we were developing a membrane technology that can effectively extract the dissolved methane in wastewater. So the principle is quite simple. So we placed this non-wetting membrane between the feed wastewater that contains dissolved methane, and then on the other side we placed an organic solvent that has high methane solubility. So because of the solubility difference, the methane is extracted into this through solution. That's how the dissolved methane can be harvested. So using this approach, we were using the food wastewater leachate that contains very high contents of dissolved methane. We were we were able to get more than 90% of dissolved methane recovery in this using this approach. So, for example, this is the methane contents, methane normalized methane concentration from the beginning and at the end of the experiment. So we were able to demonstrate more than 90% methane recovery at different temperatures. And surprisingly, after this experiment, even though we were using very dirty food wastewater, so methane was quite clean even after those, even after the 90% of methane recovery, and which is in stark contrast to exactly the same membrane that is used in existing other methane recovery processes. So I think that we think that this is quite promising approach to harvest methane from any water sources. And we use a similar approach to selectively recover ammonia from wastewater as well. So now let me get back to the first slide again. So I hope I showed you a couple of examples of membrane technologies that we are developing for zero or minimal liquid discharge. For the resource recovery, today I only showed methane and ammonia recovery for municipal wastewater, but these technologies, as well as the electrodialysis process that we are working on, will also be applicable for recovery of resources such as lithium or other metal, acid or gypsum, and so on, from the mining wastewater. Okay, so that was the end of my presentation today, and thank you for your attention, and please feel free to reach out to me if you have any questions. Thank you.